An autonomous robotic system for damage control surgery. The authors are Michael Kam, Hamed Sedel, Ori Pearl, David King, and Axel Krieger. Speaker is Michael.
Hi everyone, I'm Michael Kam from the University of Maryland, and I'm working with Axel Krieger. Today I'm going to present a work that's related to a medical robotics project, and the title is an autonomous robotic system for damage control surgery. So imagine the patients have an injury in the abdominal area, and those type of injuries are deadly to the patient because the patient might lose too much blood and die really quickly. For here, up to 29% of the pre-hospital trauma deaths are potentially survivable and are attributed to the uncontrolled hemorrhage. For those type of injured patients, the first hour after the trauma is critically important for the survival. Without a proper treatment for those patients, the mortality of the critical injured patient will increase by 1% for every 3 minutes. Consequently, effective and early hemorrhage control is important. For those type of patients, damage control surgery comes to play. What damage control surgery does is it involves early limited surgical interventions to control the hemorrhage until the patient is evacuated and have sufficient physiological reserve to undergo the definite repairs. However, patients with abdominal injuries are most really difficult to handle because they are non-compressible injuries, so you cannot purely just apply the tourniquet or apply external compressions to stop the internal bleedings. For example, if you have an injury in your livers, usually the livers will bleed very fast, and if you don't take action as soon as possible, they will probably lose too much blood and die. One of the collaborators from Dr. Kim from General Hospital in Massachusetts have developed methods to rapidly control the abdominal hemorrhage with injection of the cell-expanding polyurethane forms, as you can see in the figures. Once injected into a body, the form will quickly expand and fill up the abdominal cavity, and applying stabilizing pressures to stop the internal bleedings. Successful delivery of such forms relies on experienced surgeons to first access the abdominal cavity with a small incisions just below the umbilicus and inject the form using a delivery nozzle. However, accidents in remote scenario or casualty on the battlefields, trauma surgeons might not be immediately available, and there's no time to evacuate the patient to the surgeons. So our idea is to build up the robotic system to perform the injection test to control the hemorrhage when there's no surgical cares immediately available. And with such systems, a medical evacuation vehicle can fit with it, and surgical platform can be deployed to the remote area when there's needed. So the research objective of this project is to develop a robotic system for autonomous hemorrhage controls. And here are some basic building block diagrams, building blocks that we have in our systems. First, we need a tool to perform a self-expanding forms. And we need a camera to guide the robot system to where you need to perform the task, and an algorithm we implemented in autonomous to detect the umbilicus locations, and also a software system to control the robot system to move and perform the task. So the goal of this, the idea of this robotic system is to have the ability to detect the umbilicus and perform the form injection test autonomously. So here are the figures showing here is the robotic system that we developed and the prototype of the tools. A 7 degree of freedom lightweight robot arms is used as the surgical platforms. The tool contains of the containers holders, motor packs, and the camera holders, and the nozzle holders. So the container holders holds the foam containers and connect it to the tool itself. And the motor packs with the linear motor includes the encoder that precise positioning with using the equals-to controller. And once the linear motor pushes the tool tip, the tip on the foam containers, the foam will release from the containers and travel through a connecting tube into the nozzle. A nozzle holder holds the mixing nozzles that deliver the foam into the test subject. And the camera holder holds the RGBD camera, which is placed at the back of the tool. A human torso covered with the color-printed skin color robot and a color printed umbilicus is used as a test subject. We use the support vector machine binary classifier to detect the umbilicus from the 2D image. We prepare the training data with total of 5,299 images with 64 and 64 pixels, labeled as the umbilicus and non-umbilicus to train the SVC. And histogram of the oriented gradients is also extracted to use as an input. It allows the detectors to detect the umbilicus in skin tone. And scikit-learn package in Python is also used for training and testing purposes. And once the SVC is trained, then we're able to use it on the online detections, as shown in the bottom figure. The image coming from the RGBD camera, shown here, and fit into the trained SVC. And the training, it will apply the search boxes throughout the entire images and find the positive detection boxes that best fit the SVC model. All of the positive detection boxes are then gathered to generate the heat maps, and any concentrated area on the heat map will consider as an umbilicus. The block diagram shows the control software that we have. First, the RGBD camera stream the image into the systems, and using the trained SVC to detect the umbilicus on a 2D image. We use the existing 2D and 3D registration methods from the drivers, and with using the point cloud library, we were able to get the 3D position of the umbilicus. An offline eye-in-hand calibration is done to transform the coordinate systems from the camera frame to the robot frames. Once we have the 3D location of the umbilicus in the robot frame, a trajectory generator and the planners generate a trajectory between the initial robot position to the target point. The kinematics and dynamic libraries solve the inverse kinematics to transform the trajectory to a joint space. The joint space trajectory then feeds to a low-level controller, and it uses to move the robot. And all of the systems are integrated in the robot operating systems. So for the initial testing, we conduct 2 tests to evaluate our systems. One is the accuracy test of this, to test whether the accuracy of our system in reaching the target locations. We conducted the total 4 tests was conducted, as shown in the table 1. First, we have the reference point, which we place the umbilicus on the target on the phantoms, and we use the robot to locate the position as a reference point, which is the actual position in the robot frame. We then use the system that we develop, and use the 2D image to detect the umbilicus, and then using the control system based on the method we mentioned previous to move the robot to that locations and mark it as an actual position that the robot actually reached. The targeted accuracy is defined as the distance between the reference and the location where the robot actually reaches. And the average targeting accuracy was 7.71 plus minus 0.69 millimeters. The second test we conduct is the form injection test to evaluate the feasibility of our system. First, the 2D image, grab the image, and using the registration methods to find the 3D locations of the umbilicus. The robot controller then took the 3D locations and moved the robot to the position above. And with the translational motion command in -z directions, the robot penetrated the nozzle into the test subject. And with the signal triggering the linear motors and pushes the foam container tip, the foam successfully released from the containers and traveled to the tube and injected to the test area. So, a few remarks here. So we aim to develop a system that can perform autonomous injections for hemorrhage control. The system successfully detected umbilicus and performed the full injection test to the test subjects. Although the targeting accuracy is not in sub-millimeters, but the robotic system demonstrated early feasibility of performing autonomous hemorrhage control. Since this system is still under development in the really early stage, there are a lot of future works that we have to be done, and also in order to make the system more versatile. For example, we need to have an additional device to penetrate the subject. right now in the experiment we only use the nozzle, which is to penetrate doing the penetrating task, which is not feasible in actual situations. And also force feedback is also needed when performing such injection tests, because since right now we only use the hard-coded distance to stop the robot moving, which is also not practical in actual situation in terms of the safety. So here are my references and questions.
Thank you. Any questions for the speaker? I had a quick question to ask about the table that you showed with the targeting accuracy. So I saw from the target point that you had, all the X, Y, and Z values are always lower than. So you are never overshooting. So is there any, is that due to some artifact of your system?
So for this
thing below, that's what I'm asking.
Yes. Right. So we're thinking that one of the issues we're thinking why we have this kind of error is because we didn't do well for the hand calibrations. At the time, we are trying to explore how we should complete that, but I think we might need to do some more further study for that in order to increase the accuracy. Because when we're targeting the locations, the robotic system that we have is really accurate. So the only thing that could cause this error will be the camera frame to the robot flange that is not correctly anchored. So that's something we have to improve in the future.
Hello, I like the presentation. I just had a quick question. I was kind of not clear on what is the reason that this is more advantageous as compared to doing it by hand, and how would such a robot be deployed in the field?
Right. So for the collaborators, we developed a form. They have developed a tool for the hand guide. You can use it to do the foam injection by hand. But sometimes the reason is there's if you need to have that done really quickly, and sometimes if there's no surgeon there, then you probably have different person need to operate those tasks. And different people have variability depending on different individuals to operate the task. So we're thinking that once the robot can perform such tasks more consistent than the human, then it can do the task without having the different people to perform tasks.
I just have a question on a follow-up question. How fast were these motions performed then?
Well, so the robot is actually operating the teaching mode is not in the fast moving for the industry. You see moving really fast. So all of the tasks will be done, and we also add some delay to ensure that we don't break the tool or something. So I think all of the tasks complete tasks for running that will take 60 seconds for detecting and move the robot and insert it and penetrating and inject the form.
Then won't directly injecting by hand be faster?
Right. We can once we have we're sure that the robot can do it fast, then we can increase the speed, reduce the delay and be faster, of course.
Hi, I had a question regarding the accuracy, the error that you have here. It's around 6 to 7 millimeters. In a clinical setting, what is the acceptable error range that has to be performed?
That's a good question. So, I'm not sure for the actual clinical. It depends on the application you're doing. If you're doing the anastomosis task, probably this is going to be too large for you to do the task, doing the suturing. But for this one, since you are injected into a location, it's even if you have 10 millimeter difference, it's still going to give you to the access to the abdominal area. So even if you have a little bit offset, but you're still going to inject the form in that area. So it depends on the applications.
Thank you. This then brings up to the end of the first session.